So I'll be talking about how we are carrying ENIAC's legacy into silicon and have done so. So what we'll see is that ENIAC's architectural ideas are alive and well in today's FPGAs. As we've heard this morning, as you're familiar, sort of Eckart and Mauchly's successor machine, the EDVAC, has in many ways been a much more direct path to today's microprocessors, which we're all familiar with. I'll talk about sort of why that was the thing that made sense at the time. We'll also see that in the intervening time, we've had decades of Moore's law capacity scaling, and that decades of scaling has led us to a point where this ENIAC or FPGA architecture is actually more relevant today than ever. And you got hints of that in Professor Patterson's talk, as he talked about today's accelerators that we're using in order to move forward beyond the end of Moore's law scaling and the limits of microprocessors. So since it hasn't been done, I'll do a quick comparison so you get to put in perspective kind of where we are today versus where we are 75 years ago. What has 75 years of computer engineering done for us? So if we look at ENIAC at its time, it could do 3.3 million adder bit operations per second, and it fit into 1,800 square feet, as we saw. I'll restate that for comparison as 167 million millimeters squared. By comparison, one of today's FPGAs can perform 3.6 million adder bit operations per nanosecond rather than per second. So that is an increase of 10 to the 9th, right? A billion times increase in computational capacity, computational throughput. And it does that in 1,400 millimeters squared, which is 100,000 times smaller than the thing. So a total of 10 to the 14th more computational density than we had before. But we're still holding on to much of the same spirit of the ENIAC machine. And we'll see that these kind of changes that have led us today leads us back to exploiting many of the principles that ENIAC first demonstrated. So we saw a version this morning. Here's a quick review for those that weren't with us, or just to remind you. ENIAC was a data flow machine. It had parallel operators. Here's a picture from Goldstein, but I'm going to switch to a redrawing by Professor von der Spiegel and one of his students that maybe is a little bit more legible. We can see here that it has many 20 parallel accumulators, a multiplier, divider, and square root unit. We also see that it has these programmable function units shown here in the middle, also in the background on Jeannie's talk this morning. And here's a version here. This programmable functional units allowed you to go in and flip switches in order to program up a mapping between some input and some output. It had flip-flops and accumulators. Here's a picture of accumulator 18 from the exhibit here at Penn. This panel here is accumulator 18. It had, as you see, it had this specialized multiplier, divider, and square root unit. So it's specialized hardware. And you wired communication up between things in order to program up the computation. So you program things up by setting the constants, setting the values of these lookup tables with the switches, and wiring between the operators. So just as a quick overview, so we can see that all these elements are showing up in today's FPGAs. We can wire FPGAs up as many things, including data flow machines. They have parallel operators. We have programmable lookup tables that we use to program the functions. They have flip-flops. They have multipliers and accumulators, including dedicated multipliers. They have programmable interconnect to wire between communications. Now, as Mitch pointed out this morning, ENIAC only had 10-bit accumulators. So today's FPGAs have a lot of integrated memory, which is a big advance over that. The FPGAs are programmed much at a low level in the same way as ENIAC. You set constants, you program the lookup tables, and you wire between the operators. But the important thing to understand about kind of where we were in the 1940s, I would say that we were in the in the domain of resource poverty in the 1940s. We had very few resources that we could put into these things. So by those standards, ENIAC was actually a very extravagant machine. It was extravagant, it was parallel, it had multiple copies of each operators. As we've heard, it has 18,000 vacuum tubes and took up a large room, 1,800 square feet. In that context, EDVAC, the successor, which was a stored program processor that didn't have parallel things, it was sequential. It had only 6,000 vacuum tubes, so it was a more economical machine. It only took up about 500 square feet, right? So almost a factor of 4 smaller than ENIAC. So this was important because you could have more of them. More people could have them, and more computation could be done. So this economy in this era of resource poverty was very important, and that's why EDVAC was sort of the pattern that took forward for computing in the late 1900s, if you will. This became equally important when we started to move into silicon, because when we moved into silicon, the first thing we could do was put a few transistors on there. We built them up. Finally, in the 70s, we hit the point where we could put 2,000 transistors on a silicon die. And at that point, this EDVAC style stored program processor was the important thing, was that allowed us to build sort of an interesting programmable computation on top of this very resource limited silicon. Now, what we've had since 1970 is we've had 50 years of Moore's law scaling. And over 50 years of Moore's law scaling, we've gone from 2,000 transistors on a die to over 50 billion transistors on a die. So we've had 10 million times, 7 orders of magnitude growth in capacity. When you see that kind of growth in capacity, perhaps we've moved out of our era of poverty, in fact, into an era of abundance. So now if you look at it today, a modest die, like the one that you have, like the Apple A13 Bionic that you probably have in your iPhone or iPad, well, this modest die is 8.5 billion transistors. It includes 6 stored program processors, 64-bit ARM cores. The small ones take up 0.4% of this die. The large ones take up 3% of the die. As you can see, all of them together still take up a very small fraction of the die. So we now live in this era of abundance where it's not necessary to be so highly sequentialized in order to save resources. Instead, we can now use those resources. We can now use the parallelism in order to get more computation and more efficiency out of our resources. Now, as we saw that in ENIAC, you wired things up by plugging cables. And so you see very prominently in this picture with these ENIAC programmers programming it up, the wiring cables, and it was configured by flipping switches. And you see our ENIAC programmers here flipping the switches, putting a program in. The move to integrated circuit technology has allowed us to change that. We can now configure things by setting memory cells. We can control how the thing does by programming up muxes and programming the contents of lookup tables. And all this can be done just by loading memories, just by loading memory bits. We've removed the need to physically configure the machine, which was certainly an impediment to the early ENIAC programming that drove stored program processing at the time. So with that, let me give you a quick overview of field programmable gate arrays today. Field programmable gate arrays are based around programmable gates. They're essentially, they have these configurable bits. We can use those configurable software loaded bits to program up the lookup table to perform any function of some number of inputs. This one it shows with a 2-input function. We have an optional flip-flop, so you got your flip-flops there as well. And then we use the same building blocks to build interconnect. We use muxes to provide the programmable wiring, and by setting a configuration of bits, I can choose which one of these inputs I can connect to the output, hence programmably connecting together the different units within the block. We put those together into an array, and so here you get the name. It's a gate array. It's an array of gates. Each of the gates is programmable, as we've seen in the previous slide. So you have these programmable gates, and then these programmable gates have interconnect between them. Here you see XY routing. You can think of these as streets laid out in a grid pattern in order to connect the output of one of the gates to the input of another gate. and that programming is and interconnect is provided entirely with these programmable muxes, as we illustrated on the previous slide. Now, that was kind of what a FPGA looked like 25 or 30 years ago. I've gotten a little bit more sophisticated since then. We grouped the LUTs together into clusters, kind of like houses on a block. So we only put roads between the blocks of LUTs, the blocks of houses. We've added dedicated multiplier accumulators to them. So some of the blocks will have these dedicated multiplier accumulators, and we've added embedded memories. So we have large scale memory storage on the device. But it still shares that same basic organization and architecture. So how do we compute with these things? Well, typically what we'll do is we'll build specialized spatial pipelines for our computations. So a collection of wiring together those LUTs and multipliers and accumulators in order to customize, wired up to a particular computation. So we can build a programmable accelerator that's targeted at your particular computation that you need to perform. We can also build sort of custom engines and replicate many of those engines over the resources that we have on the FPGA. So here shows sort of one where we can customize how we store the data within the computation and customize the computations between them for some fancy graph processing algorithms. Just to give you a flavor of where today's FPGAs are, here's the one that I summarized at the beginning, an Intel Stratix GX10M. It runs at a gigahertz. It has almost 13,000 completely independently accessible memory blocks, over 2 kilobytes each in them, over 7,000 multiplier accumulators. Compare that to the 20 accumulators on the ENIAC. Has 835 gigabits per second of I/O, and about 3.5 million 6-input LUTs that can be used and programmed together wired together to perform any computation. And all this is done in 1,400 millimeters squared of silicon. Now, programming ENIAC and early FPGAs, frankly, is tedious. You had to plan out the operators. You had to make them fit within the available resources. And when you were resource poor and you only had 20 accumulators or you only had 100 LUTs, that was a real challenge often to fit there. You had to wire them up. You had to figure out how they're connected. My background here shows a programming chart for the ENIAC where you had to think about which buses to route things on and how to connect the stuff up. Effectively, in both these cases, you're designing a custom circuit for each computation at the gate, accumulator, adder, multiplier level in order to make the thing work. And the ENIAC programmers demonstrated that it was possible to program these sort of things, as did many early FPGAs pioneers, but it was certainly painful and difficult. But we've had 75 years of computer engineering contributions since then, such that we can been able to raise the abstraction so we can now program at much higher levels, including writing programs in C. And so here shows an example where I can write a C program, and then I can automatically translate that through compilers and place and route EDA support into the kind of design that we saw earlier. So there's obviously a lot more that one can say about this. Here's a couple of references to follow up on if you want to learn more about ENIAC or see a little bit more about today's FPGAs and how those things relate. What we've seen here is that the spirit of ENIAC really lives on in today's FPGAs. And the things that made ENIAC sort of less attractive than EDVAC in the 1940s have largely gone away because of scaling. And because of those scaling issues, we're now at a point where the kind of parallel data flow spatial architectures that ENIAC and FPGAs represent are more important than ever. And we'll see that we are seeing these FPGAs taking a more important role alongside sort of more EDVAC-like microprocessors in our large-scale computing today.
Thank you, Andre, for that great talk. I think we do have at least one question for you. So are FPGAs taking advantage of any 3D IC technologies?
I think the short answer is yes. I mean, what we're seeing, the version we're seeing today is what you would call technically called 2.5D. We're seeing that that dies are being stacked on top of a silicon interposer, and they're using that in order to build larger die, build larger computations, build them more economically, and to mix and match them with high bandwidth, with memory type designs. So you're seeing those in sort of mainstream devices today, and looking ahead to kind of chiplet type further designs with those sort of things moving into the future. People have experimented with just stacking FPGAs on top of each other. That has not become a mainstream technology yet, though we have seen people do some early experimentation with that.